So we'll finish up shear today, I think. So let's kind of have a look at this again. You know, what causes this? First thing I want to mention is, I guess, is that shear is caused by a bending beam, and different sections of the beam want to bend a little differently, and that can result in building up stresses along the long axis of the beam. So shear would build up like along that line there. Okay. And it's kind of like, think of a book bending, think of the pages of the book. They want to slide like you're seeing over there, but the atomic bonds hold them together kind of in that right angle configuration that you see there on the left. So they prevent that motion from happening. So you get stress that builds up along those long planes, and that's the type of shear we're talking about. So the shear is really a function of the bending stress in there. It creates different forces on either side of a plane there that tend to try and split or make those planes slide, is what it does. So you're kind of looking at those two forces and how they're different, and they create that shear stress. And we kind of go through this long rigmarole here on developing the equation. We first go, it's kind of interesting because first we go to the bending stress, which is a function of the moment. You know, the normal bending stress is mc over I or my over I. But then we look at the change in moment with respect to the distance x, which is dm dx, which takes us right back to shear. So we kind of go through moment to get those two forces, and then take the derivative of moment with respect to that dx that we're working our way down the beam with. So we end up back at shear. And then we end up with this equation here that the shear stress is VQ over IT. Okay. So V is the shear off the shear diagram. Q is this first moment of area, which kind of gets back to that idea of bending stress on a vertical area, right there basically. And then, whoops, I didn't put that in the right spot, right there. And then I is the moment of inertia for the entire beam cross section, and T is the thickness of the beam. Okay. So that's how we derive that. So what we end up with then is tau max occurs at the neutral axis. The minimum tau, the minimum shear stress, occurs on the edges of the beam. So that's a shear failure you're looking at there. So any questions on that? Just a basic idea of it? It's kind of the idea of it. All right, now the VQ over IT is the general formula for shear anywhere you want to investigate in the beam. The maximum shears vary, they depend on the type of beam. Rectangular, it's 3V over 2A. For a circular beam, that's rather unusual, but if you have such a thing, it would be 4V over 3A. And then a flange beam, you just look at the average shear in the web is what you do. So that's the shear force V off the shear diagram divided by the thickness of the web divided by the height of the web there, okay? All right, and then we went through an example here. Why don't we have a look at this again? What we've got is we've just got a beam that we've got it loaded as shown, simply supported, 4 meter span. We've got a 36 kilonewton load over there at 3 meters from the left. And we want to know a couple of things. We want to know the maximum shear stress, and also we want to know the shear stress at point C1. Okay, so I've got C, which is 1 meter over from the left-hand support, and then point 1 is 80 millimeters up the beam there, okay? So we've got something like this in 3D, and I'm showing, C and 1 in different locations, I guess you'd say. So we got that, and then we got that. We're applying that load, so C1 is over here. It's the shear right inside the beam, right there, or across the beam. It's 1 meter over from A. That's the idea of C1. Okay. So I'm showing you C on where I've got a line representation of the beam, 1 meter over from A. Then I show point 1 on the cross section of the beam. Okay. So that's the What's going on there? Right? So both the bending stress and the shear stress, I just look at the formulas. I just try and find the things in the formula, then plug them in. So what I want to know is V, Q, I, and T to find the shear stress at point C1. So I can kind of run through that there and kind of get to that stuff. So what I've got is I draw up a shear diagram, and I get 9,000 is the value of shear at point C. So that'll be my V, okay, 9,000 newtons. The thickness of the beam's easy enough. It's just 200 millimeters, which is 0.2 meters. And I is just BHQ over 12, so it's 0.00045. Okay. Now the last thing here is Q. Now Q, I just want to encourage you to get that one figured out, because I'm sure there'll be one of these on the final, and you want to be able to work through it. And Q seems to, in the past, have been a stumbling block for people. So let's be sure that we understand Q and what it is. And this is the slide I had. You could screenshot it if you're online. I handed out a copy of this. I don't think everybody have a copy of this. I gave it to everybody. All right. So what we've got is Q is AD. Okay, I think of A as being the area that would shear off if the beam failed. And D is the distance from the neutral axis to the centroid of the area that would shear off. So if the beam fails at point 1 there, the shear line will be right there. Think back to that slide we were just looking at, where we had the, right there. So this is the shear line. What I mean, if this was C1 right there, point 1 would be right there, and then it would be the area that I've outlined there in purple, okay? That would be the area. The distance would be that red distance from the neutral axis down to the centroid of the purple area. That's what we're doing, all right? So we want to be sure that we understand that. We can apply it. All right, so the area that would shear off would be the 200 millimeters, 0.2 meters by the height. It's 0.08 meters above the, excuse me, the bottom of the beam. That's 0.016 square meters. Then we would measure down from the neutral axis to the centroid of that area. And so what we have there is the total beam height is 0.3 meters. So half of that from the centroid down to the bottom would be 0.15. But we're at the centroid of an 80 millimeter high area there. Half of that is 40 millimeters, which is 0.04. So to get the distance from the neutral axis to the centroid of that area, we take 0.15 minus 0.04. And we get 0.011, or I'm sorry, 0.11. Okay? So that's the distance from the neutral axis to the centroid of the area that would shear off. Okay? So that's what we got on that. So what we do then, we multiply those two things together, A and D, we get 0.0176 cubic meters. It's an odd unit, but that's what that is, because it's an area times a distance. It's called the first moment of area. Okay. It's kind of like the top of the centroid formula. It's kind of what it is, the area times the y bar to the centroid of the area from the neutral axis. Okay, that's kind of what it is. All right. So are we good with that? We're good. All right. So we got everything, so that's how I think about running these formulas. I just look at the formula, I just figure out each one of the terms in the formula, and you just plug them in. And what you would get for the shear stress there is 9,000 times 0.00176 divided by I, which is 0.00045, and divided by T, 0.2. And that comes out to be 176,000 newtons per meter squared. So that's the shear stress at that particular point. Okay. So that's how you do that. That's how you find the shear stress. Now there's a few other things you can do with shear stress, but we'll kind of start there. Okay. So that's step one. That's the general formula for shear stress for a bending beam. Okay. Now in this problem, I also said, what's the maximum shear stress? Okay, this is 3V over 2A. It's a lot simpler than this whole business. You just take V from the shear diagram. A is the total cross-sectional area of the beam. Take V over A and multiply it by 3/2, which is 1.5, and that's all there is to it, okay? So you just find the area of the beam, 0.2 times 0.3, 0.06 square meters, and take 3 times the maximum shear, which is on the right there. It's 27,000, divided by 2 times the area, 0.06, and you get 675,000 newtons per meter squared. Okay. So that's the last bit there. Okay. Quite a bit more than the shear that we found at C1. All right. So if you're going to design that beam for shear, that's the value you'd use right there. So that's the deal with that. All right, let's say on this next one here, we want to find tau max for this beam. That's an I-beam, so it's tau average there would be V over TH1. Okay, and that's approximately equal to tau max. See, the reason your safety in this one comes about from the fact that you're just pulling the web out. The shear in the flanges is pretty small because the shear increases as you get closer to the neutral axis. So to get the design value for an I-beam, you just take the total shear force and assume it's borne, in this case, by the web, and you just find tau average for it. Okay. So why don't you just take a minute and get a shear diagram given the loading diagram there. What's that going to look like? Just for a little bit of practice on that. I got the reactions there for you. So remember, when you see an area like that, calc it up. And that's the change, is what that is. Something on that. Something like that. So that reaction takes you up to 30 kips, and that area there is minus 120. That takes you down to a negative 90. That's a straight line.